Record and started. So what we're going to look at today is step into the RLC series circuit. So we'll begin by looking at an example. So if we have a 1 ohm resistor, a 100 Henry inductor, and a 0.1 farad capacitor connected to step voltage of 10 volts. We're looking to find an expression for IT. Yep. So we're looking to solve that circuit. So remembering back, first thing we have to do is write an expression.
Oh my God, Callum, what are you doing?
Sorry, can you hear that?
Obviously,
Yeah.
you twat.
I'll put it in the other room. Hang on. There we go.
Yeah, Callum, you're disturbing my lesson. Right, we've got to write an expression for Z in S space. We could do that. Well, you tell me what it is, someone.
That is ZS.
When we transfer a resistance into S space, we just end up with, if you've got your table, the number. So it's however many ohms it is, we drop the ohms, we just have 1. And then they're in series, so it's plus. We do an inductor, it's L times S, so it's going to be 100S plus, and then the capacitor is 1 over CS, so it's 1 over 0.1 S. Remember that?
Yeah.
Yeah.
Yeah. Okay. Now, the second thing we need to do here is we need to express as a single fraction with a common denominator. So in order to do that, we can express this as ZS, and if we want the constant 1 to have a denominator, it'll have to be 1. So you'll agree that 1 over 1 is still equal to 1. Yeah. And if we put 100S over 1, we've still got the same thing as up top. Yeah. And then plus 1 over, we've already got a fraction there. Yep. The common denominator here is 0.1S. So if we
That was a
if we multiply the bottom by 0.1S, we also have to do that to the top. Yeah. Here, 0.1S, so we've got to do the same thing to the top, 0.1S times 100S And then here it's plus, and that stays the same because the denominator is already 0.1s. Everybody follow that so far?
Yeah.
Yeah. That means we can write the whole thing with one denominator of 0.1s. Yeah. Here is 0.1s plus, and then this multiplies out to 0.1 times 100 is 10, so that becomes 10s squared, yeah, plus 1. Do you all follow where that comes from?
Yeah.
Yeah.
Yeah? Sure?
Yeah.
Right.
13% sure.
13.
What being a dick for?
Shut up, Callum.
Wow.
I'd say 13% is not very sure, really, but right. So that's our expression for ZS. New page for me. So we've got had this problem this morning. Here we go. So at the moment, we've got the expression ZS is 0.1s plus 10s squared plus 1 over 0.1s. Yeah. In this, Vs is as 10 volts, so as 10 over s. Agreed?
Yeah.
Oh, yeah.
Our 10 volt step is expressed as 10 over s. So we can now write Is as equal to Vs over Zs, which is 10 divided by s, all divided by 0.1s plus 10s squared plus 1 over 0.1s.
Oh my God.
Yeah. Oh my God.
Fraction over fraction over fraction.
Now we got
Oh, Sam.
one fraction divided by another fraction.
That's
So
right.
how do we simplify that? We keep the 10 over s up the same way. We multiply by the other fraction turned upside down.
Times 0.1s.
Callum, shut up.
Listen, you.
Okay,
What is that middle? Was that 10? I can't see what that says.
that's 10.
10.
I mean, that's not so easy as you might think to write on a glass screen. Is that better?
Yeah, thank you.
Okay, so then we multiply that out. We end up with 10 times 0.1 is 1s. I'm going to write 1s there on the top, and on the bottom we've got this s times 0.1s plus 10s squared plus 1. All agree with that?
Yeah.
Yeah.
And what we can do now, let's change colour, is we've got an S here and here that cancel out. Yeah. Therefore, IS is equal to 1 over 0.1 S plus 10 S squared plus 1. Yeah. Now, have a look in your table of Laplace transforms and see if you can see anything that looks like that expression in the table.
Oh, hold on. Oh.
A squared term, an S term, and a constant in a fraction.
Oh. A what? A what? I don't know what. Hmm?
That's got to have. It's got to have.
One minute.
Term with S. It's got to have a term with S squared. It's got to have a term with S to the power of 1. It's got to have a constant.
Mind.
I don't know.
Okay. Well, I weren't expecting you to recognise that there is one,
Now which one to use?
but there is. Okay. But having said that, there's a bit more to do to be able to get it in the right form. Okay. But we've currently got hang on, different colour. IS is equal to 1 over 0.1s plus 10s squared plus 1. Yeah. If you look in the table, you've got the damp sine. We've got e to the minus at sine omega t transfers backwards and forwards. So this is t space, and in s space it is omega over s plus a squared plus omega squared. Right?
Oh,
You got that?
so wave you're going for?
Yeah. Now, we need to look at it in detail, but if you was to multiply out the s plus a squared, you'd end up with a squared term, an s term, okay, and constant, and then the remainder of that constant can become this omega squared, because omega and omega squared are constants as well. They make up this omega in the damp sine wave over here. So we're looking at an expression that is a damped sine wave. Yeah. If we multiply out the denominator, so if we do s plus a squared plus omega squared, what that is s plus a times s plus a plus omega squared. Yeah. We get S times S is S squared plus 2SA plus S squared. Yeah. And then omega squared. So we've got a squared term, this term, and these make a constant. Do you see that?
Not very clearly.
Why do them ones make a constant and not the other ones?
Because
Make a constant and the others don't?
because in this expression here, Callum,
Yeah.
I and omega are constants. The variables, when we transfer back, I over here, I and omega are constants.
Oh, okay. And S isn't.
The variable will be the I at t that you're saying this is equal to, and the time t is the independent variable, isn't it? Remember, we're looking for an expression it is equal to. Yeah. So t is the independent variable, and I is the dependent variable. I and omega are constants. Omega, as you know, in a sine function is the frequency in radians per second. Yeah. And this I up here is the time constant for that exponential decay. All right. This function, if you graph and you finished it, it goes like this. If that's the axis, it's a sine wave that diminishes. It's a damp sine wave.
Right.
Yeah. So you'll see that eventually. All right.
Okay.
But if we compare, right, what we've got here, 1 over s squared plus 2as plus a squared plus omega squared, how does that compare with our expression we had earlier, 0.1s plus s squared plus 1? We've got, using different colours, we've got here a squared term, yeah. We've got a term in S, which is here, term in S, yeah. And we've got these two added together that can make up the constant.
Okay. Yeah.
All right.
See that.
And when we look at what we're going to look at next, how the perfect square works, you'll see where all that comes from and that likeness. Yeah.
Somebody's put a pissing lawnmower on. Get away.
So the perfect square. So we're going to break out from Laplace transforms in a sense at the moment and say s plus 2 all squared is an example of a perfect square. Yeah, we've got a variable term plus a constant in brackets, and that's all squared. If we take s plus 2 squared, we say that's equal to s plus 2 times s plus 2 which is s squared plus 4s 2 times 2 is 4. Yeah? Equally, if we do s plus 3 squared, that's s plus 3 times s plus 3. S squared plus 6s plus 9. Yeah?
Yep.
4 all squared uh, 8s plus 16. Yeah? Is there a pattern you're recognizing yet?
Yeah.
S plus 5 squared is s plus 5 times s plus 5 s squared plus 10s plus 25. If we read the general version, s plus a all squared is s plus a times s plus a equals s squared plus 2as plus a squared. Yeah?
Yeah.
Okay. So, can you see that if a is this number here, so if we compare the s plus 5 one with the general one underneath, right? S is what it is. But in this term here, this number is 2 times a. So in here, that 10 comes from 2 times 5. Yeah, so that number here comes from 2 times this 5, and this number here comes from 5 squared. See that or not?
Yeah.
Yeah.
Yeah? Right. Is this a perfect square? S squared plus 12s
Oh,
plus 36. Can we write that as a perfect square? Anyone? Remember, what we need to be able to do is write it as s plus something all squared.
6.
Yeah, because we've got the square root of 36 is equal to 6. If we get to 36 from this by squaring 6, we must get back to the 6 in here for square root of 36. Yeah.
Mm-hmm.
And then this 6 also comes from 12 over 2. If we doubled 5 here to get the 10. So if we've got 12 here, we must half it to get the 6 inside there. So that's going back the other way. It's going back from a quadratic effectively, this is a quadratic expression, isn't it? Squared term, S term, constant. Going from that to a perfect square is the process of halving this number and or square rooting that number to get this 6 in here. Yep.
Yep.
Okay. Everybody okay with that?
Yeah.
Yeah.
Right. Perfect square can be used to solve quadratics. If we have s squared plus 12s plus 36 equals 0, remember what we're trying to do when we solve that. If this is the graph of that, we're trying to find the values of x where y is equal to 0. And they can have 1 or 2 solutions or no solutions. You remember that? Yeah.
Mm-hmm.
So we've already seen that we can write this s squared plus 12s plus 36. We can write it as s plus 6 all squared. And that's equal to 0. Yeah. If we then square root both sides, so square root of nothing is nothing. Square root of s plus 6 squared is s plus 6. Agreed? Yeah. Therefore, s is equal to minus 6. One solution. So that actually that function sits on the x-axis. It's only got one root. Yeah. Can we solve this one? S squared plus 12s plus 36 equals 9.
Have you got to make that equal to 0 first? So you'll have to move the 9 over to the other
Not
side.
necessarily. Not necessarily. If you subtract 9 from this 36 count, you won't be able to make it a perfect square.
No.
At the moment, we know we can make this a perfect square, so we can write left-hand side as perfect square. So if you do that, then you should be able to solve it. Couple of minutes, and I'll tell you that it's got 2 values.
Right.
We've obviously done this. You've written s plus 6 all squared is equal to 9. And then you root both sides. So we end up with s plus 6 on this side is equal to the square root of 9 on that side. Yeah?
Yeah.
Is equal to plus or minus 3. Square root of 9 can be plus or minus 3. Therefore, s is equal to plus 3 minus 6, which is minus 3, is equal to minus 3 minus 6, which is minus 9.
Oh, okay. Yeah.
Yeah, well, everybody else follow that?
Yeah, boss.
Mm.
Good. Right. What about this one? S squared plus 10s plus 12 is equal to 0. First of all, is the left-hand side a perfect square?
No.
No. Okay. If we know is the answer, yeah. If we just consider the bit that says s squared plus 10s, could we write a perfect square that would satisfy that? Forget about the constant on the end for a minute. So based on just the s squared plus 10 part, 10s part, this could be written as we've got, if we write that as s plus 5 squared, okay, then what does that multiply out to?
That'd be s squared plus 25 s, wouldn't it?
Yeah. Yeah. So we've got we can write it as with a remainder that is, because if we s plus 5, what that equals is, yeah, s squared plus 10s plus 25. Yeah, but we've got to make that 12. So if we put minus 13 in there, we're then back where we started, up here. So we can write, because s plus 5 squared gives us 25, but we want 12 as our constant, we need to take 13 off. Yeah. So the answer to this is that can be written as s plus 5 squared minus 13 equals 0. We've got perfect square, and we've got plus or minus, because it could be plus or minus, a remainder. Yeah. Okay.
Yeah.
Yeah. And remember, s plus a squared omega squared s plus a omega squared a s omega squared. Seen the form now of that expression that we're looking for. So we had an expression for I that had a denominator with a squared term, an S term, and a constant. If we can write that in this form down here, then we can transfer back to the time domain. Confusion or not?
No, that's not too bad.
Well, can I just ask one thing? Where does the I might not have been paying attention, but where's the 25 gone to end up at that minus 13?
Oh, sorry, Callum. When we write the perfect square here, let me change colour again. Blue. The perfect square bit, yeah, that bit,
Yeah.
multiplied out gives us that bit.
Yeah.
Yeah. So that's a perfect square, but our expression hasn't got 25 as the constant up here. It's got 12.
Okay. Yeah.
So if we take 13 off, we end up with 12. If we take 13 away from 25, we end up with 12.
Yeah. Yeah.
Okay.
So that 5 is contained within that S plus 5 squared bit, isn't it? Because that's not actually a constant. It's
Yes.
within
Yes.
that.
Yeah. Because if when you multiply the S plus 5 back out, you do the last thing you do is 5 times 5, which is 25, isn't it?
Mm-hmm.
Yeah.
Yeah.
Okay. So one more example we'll look at is about this one. 3s squared plus 12s plus 5 equals 0. What do you think we need to do that first so that we can turn in a perfect square? If we divide by 3 to get s on its own, s squared on its own, sorry. We can't get a perfect square until we do that, can we? So that gives us s squared is equal to 12 over 3 is 4. Sorry, s squared plus 4s plus 5 over 3 equals 0. Yep.
Yeah.
All happy with that?
Mm-hmm.
Yeah. Now we can start this off by saying we must have s, and remember the constant is half of this 4, so it's going to be 2 all squared. Yeah. We're going to get to, so if we multiply that out, we'd end up with a constant on the end of 4. Yeah. Which is 12 over 3. Yeah. So we're going to have plus 5 over 3 minus 12 over 3. We want it as thirds, so we can take it away, yeah? Everybody following or not?
Yeah.
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 You'd end up with minus 7/3.
Yeah, equals 0. So finally we have s plus 2 all squared plus, minus 7 over 3. Equals 0. Yep.
Yep.
So, in order that we can use this in the Laplace transforms, we need to be able to write that quadratic in the denominator in perfect square with a remainder form, because then this number here becomes the A, and this is the omega squared. Yeah, then we got it in the right form, right? But we need to work out a way of these recognizing exactly how we get to the 2 and the -7/3. So what I'm going to ask you to do now is express s squared, s squared with a remainder. Have a go at that one. Come on, Peter, what have you done this time?
I'm not entirely sure, really. I find this thing quite complicated, this whole square thing.
Well, we know we want to write it as s plus something all squared. Yeah.
S plus 3.
And to get that, we halve the 6, so we wrote 3. Yeah.
Ow.
If we multiplied that out, Peter,
Yeah.
s plus 3, we'd end up with a constant of 9 on the end, wouldn't we?
Yes.
Yep. So what do?
Oh, yeah.
We want to get to 4. So it must be, we'd get plus 9.
Yeah.
Yeah. But we want 4 plus -5. Yeah. So if we would, let me do that, let's just say that again. If we multiplied this s plus 3 out, we'd end up with a constant on the end of 9.
Yeah.
Yeah. But we want 4.
4.
So it must be, the remainder must be -5.
Oh,
If we just multiply this out now, you'll see what I mean. Multiplying out the s plus 3 squared term, we get s squared plus 6s, yeah, plus 3 times 3 is 9, -5 equals 0, yeah, and that 9 minus 5 gives us the 4 we had up here in the first place. Yeah or nay?
Yeah.
So we've written it as a perfect square with a remainder that gets us back to this constant 4 up here. That remainder could be positive or it could be negative. Yeah, or not. You're not answering me, Pete.
I don't know.
Let's just see if doing it in general terms helps. If we had s squared plus is plus b is equal to 0, yeah, our perfect square bit would be a over 2. Yeah, hang on, done it wrong. Let's make this a 2 a's in there, yeah. We have to half that 2 in front, so that'll just be a. And then this, to get this b, we'd have b minus a squared. That's not much help really, is it? I think that's a bit more confusing, to be honest.
Yeah, a little bit.
Let's try another example with numbers. S squared plus 3s plus 12 equals 0. Yeah?
Lost my bloody pen now.
Yes, Pete?
Yeah.
The first thing we know we can do is write this as this perfect square bit as s plus this number divided by 2. Yeah?
Yeah.
And then we know that if we multiply out s plus 1.5 squared, we get s squared plus 3s and 1.5 squared equal to 2.25. Yeah? But
Right.
we want 12. So to do that, to make this 12, we had to add 9.75. So that bit is this multiplied out. But to get this constant back to 12, we've got to add 9.75.
Okay.
All right?
Yeah.
So effectively, this number here, this 9.75, is equal to 12 minus 1.5, that number in there, squared. You see that?
Yeah.
Okay? And that's always, that method will always be the same. We can write the perfect square by dividing this constant that's in front of s by 2. Yeah? And then we take that number here squared away from this number here we had in the first place, the constant in the normal quadratic.
Right.
So that 9.75 comes from the 12 minus the 1.5 squared. A or nay?
Yes.
Yes.
Yep.
Yeah.
So what we're going to do now is go back to our circuit problem we had originally. So from earlier, we had IS is equal to 1 divided by 0.1s plus 10s squared plus 1. First thing we need to do, will you tell me?
Write it as an expression in T space. So that's what we had
No,
before.
you can't do that yet. We need s squared on its own, so we need to divide by 10.
I don't,
Yeah, so that's equal to 0.1 on the top, .01s. I'm going to do this slightly different. I'm going to put the square term first, because that'll look like what we've been doing then. It doesn't matter. So 10s squared divided by 10 is s squared. Then I'll put the s term, 0.01s, and then I'll put the constant 0.1 on the end. All happy with that, that we divide that expression by 10 to get s squared on its own.
Yeah.
yeah.
Right. Then, applying the method we've used with the perfect square, you need to keep 0.1 on the top. I'm going to write this expression here now, this denominator down here, the perfect square. So we know we've got to do s in brackets, and we've got to do this 0.01 here over 2. So that's going to be plus 0.005.
What is that squared?
All squared. Yeah. And then we got to do this number in here will be 0.1 minus 0.005 squared. Anyone done that?
Well, 0.005 squared is 2.5 times 10 to the minus 5.
Yeah, you got to take that away from the 0.1.
So it's 0. Right, okay. Minus equals 0.099975.
Yeah. Okay. Yeah. So our final expression is 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 equal to 0.1 divided by S plus 0.05 all squared plus 0.099975. Yeah?
Yeah.
That looks like omega, a constant, 0.1 as a constant, divided by S plus A is a constant, 0.005 as a constant, squared, plus another constant, which could be omega. If omega is constant, 0.1, then omega squared must also be a constant. Do you agree that we have our expression in that form now?
Yeah.
A perfect square plus a remainder.
Yeah.
Yeah?
Yeah.
This is where black. Omega squared is equal to 0.099975. Yeah. And I is equal to 0.005. And we can get omega from square root of 0.09975 is to 98.
Zero, nine.
If you square root that number, I believe you get
0.31618882.
Yeah.
what did you get omega as?
0.316.
Square root of 0.09.
Yeah.
I'm just wondering because that ain't what I got on here.
I got it as well.
No, how can that be right? How can 0.
That's got point. Wait a minute. I'm
Would there not be like another zero? Would it be 0.031?
we got to have 0.1 on the top. Yeah. So I can see what we need. If we at the moment we got 0.1 on the top. Yeah. So what we got to do is divide by if we multiply by 0.1 by 3.16, 0.316, we end up with yeah, what we need is it's been a long session, gents, has it not?
Hmm.
At least I've got a nice chair to sit on, unlike usually.
What do you mean, unlikely usually? You haven't been here for the last 3 weeks or 3
I
sessions.
meant in the classroom, knob.
Oh, you absolute piece.
Oh, you think them chairs are nice, do you?
No, not at all. I'd
Why
much rather
disagree
sit
with
on
me
my
for?
sofa like I am now.
Well, there you go then. You've just confirmed my point. You didn't need to put your 5 pence worth in to disagree with me, did you?
I
Yeah.
kind of just feel like it's a natural response to want to disagree with you, to be honest. I'm sorry.
Right, guys, if we take this 0.1 over S plus 0.005 all squared plus 0.099975, we need to have here we've got omega is equal to 0.316. So if to get that, we must multiply the top by 3.16, because 0.1 times 3.16 is 0.316. Agreed? So if we, what I'm saying is if we multiply the top by 3.16, then 0.1 times 3.16 is 0.316.
Yeah.
If we do that, we must multiply the bottom by 3.16 as well. Then effectively we'll multiply the whole thing by 1.
Yeah.
Yeah. So we can end up with 1 over 3.16 times 0.316 over S plus 0.005 squared plus 0.099975. So we got, let me just write that on another page. We've got this. We've got IS finally is equal to 1 over 3.16. Yeah. Times 0.316. That's what we said omega was. Divided by S plus 0.005 all squared plus 0.099975. Yeah, we've got a constant multiplier times a damped sine wave. Transferring back, IT is equal to, got our constant multiplier, 1 over 3.16. Yeah. And then that's E to the minus A, which is 0.005, T sine omega, which is 0.316 T. That's our final expression. Yeah.
Yeah.
Okay. And I'm just, let's have a look. It's worthwhile seeing what that looks like. So we've got y equals 1 divided by 36 E raised to the minus 0.005 x, and then it's multiplied by functions sine
Callum, where the fuck are you waving at?
0.316 x.
Oh, sorry, I forgot you could see me.
Close the brackets.
I'm waving at the dog outside.
It wouldn't surprise me if you were.
It's bloody scale. Oh, the amplitude. Excuse me, guys. Don't know anyone in Glasgow. Don't know anyone in Glasgow.
Probably for the best.
Just these axes. We have a y-axis going up to 0.1. You can't really see, it's difficult to see that the time constant is so high on that you can't see us actually, if we had a better one, it's actually doing, just go back to what you should get with a damp sine wave. Like I said, what we should see here, can't draw a straight line on this damn thing. Over time, what we should see here is a sine wave that does that, i.e. it's got a frequency of omega, but it decays away exponentially. Yeah.
Yeah.
Bit like
Okay.
Pete's hair, really.
And when we have a look at some of the other ones we have a look at with more realistic component values, that's because those component values are we started off with in the first place. Well, an ohm is not unrealistic, but the reactive components. I mean, 100 henries is a massive, great inductor, and a 0.1 farad capacitor is really big as well. So that's why you're not seeing a very fast decay away. But when we use some more realistic component values another time, then you'll see that you do get a damped sine wave. Okay?
Okay.
So between now and next time, we can go at this one.
I mean, I can't guarantee that I will, but I'll write it down.
No, okay.
You are a terrible student.
Oh, mate, I'll write it down.
Well, you can make a start now, Peter, can't you? We ain't finished yet.
I would keep this session open, Mike, and crack the whip on him until he gets it right. That's what I would do.
Well, the gentleman's got an exam to pass, hasn't he?
Damn right.
That's a laugh.
I'm sorry, Callum, did you pass the first electrical exam?
Yes.
Oh. Well, what about the other ones? You failed any of those?
No.
You sure?
Well, I failed one. What one did I fail?
I can't remember, but I know you failed one, you penis.
I failed Adrian's because that was basically because he changed the exam paper on the actual day.
Well, then how did the rest of us manage to pass?
Luck.
Yeah.
You already just passed it, Pete.
Shut up, bitch.
Have
I'm
a good-
100%.
What a load of old rubbish.
Guys, have a go at that one. And in good old Mr. Bird fashion, the answer that you should get is
All right, yeah.
IT is equal to 0.516 E. Make this a bit bigger. To the minus 1.25 T sine 4.841 T. That's the answer you should get. All right.
Okay.
And what we'll do is we'll start up next week on a solution to that problem and then take it from there.
Okay.
All right.
Sweet.
Minus 125 T. Sine.
So the first thing you know what the procedure is. You've got to get the expression for ZS in the first place, then use Ohm's law to get expression for RIS, then manipulate it using the perfect square, find out what omega and omega squared is, and transfer them back to end up with the expression in time domain. All right.
Yeah.
Just going to resume the video for a minute because going back to this bit where we ended up with how we got to that 3.16. Yeah. Are you all with me?
Yeah.
Remember,
Yeah.
going back to the slide, I'm still sharing it, aren't I? This should be a constant times omega in there. Yeah, looking at my table. So, and they call this Sorry, I call this B. We can't have two A's. So hang on, let me just change. No matter what letter we get rid of that. Get rid of that. We'll keep the bottom one as A because that's what we've been working in. We'll call this B. Yeah. So remember what this piece on the top here is equal to in our expression is 0.1. Yeah. So B times omega equals 0.1. Yeah. Therefore, the constant multiplier, we know what omega is. It's 3.16. Yeah. All right. So.
Oh.
Point one. Just getting on my day.
Just leave it. What do you want? Why did you already decide to leave that? So I thought one thing.
Right, boys, we'll put that right next week, I think. We'll run out of time.